Welcome everyone to this lecture, and in this lecture I'll be talking about the steady panel method. And so the steady panel method is basically a numerical algorithm to solve the flow around any arbitrary airfoil. So it's very similar to thin airfoil theory. However, you can extend thin airfoil theory to arbitrary angles and arbitrary wing shapes. So this method relies on potential flow modeling, and in potential flow, you assume that the flow is inviscid, irrotational, and incompressible. So if you're able to make all these assumptions, then you can use potential flow modeling, which can be very powerful. And the potential flow modeling aspect here relies on three main boundary conditions that absolutely have to be met to arrive to a physical solution. So to start off, the first boundary condition that you have to meet is the no penetration boundary condition. And the no penetration boundary condition basically says that whatever solution of the flow you meet, the flow cannot penetrate the wing. So on the left-hand side here, for example, you have the streamlines moving with the streamline moving along the airfoil, so the flow does not penetrate the wing. So here the flow is physical, but here you can see the streamline is penetrating the wing, which means that the velocity or the fluid is going into the wing and through it. And if you don't have a porous wing, that cannot happen. So that no penetration boundary condition is the first condition that has to be met, and it's really important. The second condition is Kelvin's total circulation, which basically says that in a system, circulation has to be conserved. So the total circulation in the system has to always be the same. So d gamma dt, and gamma is circulation. The change rate of the circulation in the system has to equal to 0, which makes sense. You have the conservation of mass, conservation of energy. Here we're talking about the conservation of circulation. So an example of this boundary condition is if you have a wing starting from rest, and so if a wing is at rest, there is no circulation in the system. Thus, when it starts to move, the entire system has to also contain 0 circulation. So if you have bound circulation being built up here on the airfoil, you have to have equal and opposite circulation shed from the airfoil, and that's a starting vortex. And basically gamma 2 and gamma 1 equate to 0. And this is actually seen, this is an illustration of this phenomena. This is, I think, a visualization from Prandtl in 1934, where he starts a wing from rest. And you can see here you can see the circulation around the wing here, and then you can see an opposite circulation forming. Should use a different color. You can see an opposite circulation forming here to sort of compensate for the bound circulation that's being formed on the airfoil. So that is the second boundary condition. And finally, the third boundary condition, the Kutta condition. Now, the Kutta condition basically entails that velocity of fluid is always continuous at the trailing edge, which means that the fluid should leave the trailing edge smoothly. And again, this is an illustration of what's happening. The fluid at the trailing edge here leaves smoothly, and thus this is a a good representation of the flow. Here the flow is not leaving smoothly. It's not leaving the trailing edge smoothly. You can see here that the flow goes around the trailing edge and back up again. So here you're not meeting the cutoff condition. So any potential flow solution you arrive to has to basically meet these 3 boundary conditions. Now, moving on, I'm going to go through the basic premise of the panel method. Now, in the panel method, you represent the airfoil using a series of discrete panels. Meaning that you represent that airfoil with an alternating set of collocation points and bound vortices. Now I'm gonna go into the definition of what a collocation point and a bound and what's a bound vortex in a bit, but in a sense, you take this airfoil and you simplify the airfoil to just its camber line, and then you basically represent the camber line with a series of collocation points and a series of bound vortices. So the X here represents a collocation point, and the dot represents the bound vortex. And right now, let me just go through the definitions of each and why we need each of them. So a collocation point on a camber line essentially is a point over which you enforce the no penetration boundary condition. So essentially you use these points to enforce the no penetration boundary condition and to enforce the fact that the wing has rigid walls and no fluid can go through it. So it represents the airfoil's rigid walls. Next thing is the bound vortices, right? You have the bound vortices on your camber line, and they basically their strengths are set such that the boundary conditions are met. So essentially a collocation point is a point over which you enforce a boundary condition, and the bound vortex is the tool you use to enforce that boundary condition. And I think things will become a little bit more clear as I go through an example later on. But basically these bound vortices, so we said that the collocation point represents the airfoil's rigid walls. Now, a bound vortex represents the boundary layer over the wing. So these two things are mathematical constructs here, but they represent very physical things. And so let me talk about the boundary conditions, or what boundary conditions we need to meet. Now, you have a steady panel method, which we are talking about this lecture, and we have an unsteady one, which we will talk about later, maybe a month from now or something. So in the steady panel method, you have to enforce no penetration, and you have to enforce the Kata condition. However, you don't enforce, or you don't have to enforce, Kelvin's circulation theorem, because essentially in the steady panel method, we only solve for the steady scenario. So if we have a wing starting from rest and going up to some free stream velocity, we only capture that last time step. So we don't really march our solution in time. We just look at the final solution. And thus we don't really see the starting vortex. So in that sense, we cannot capture the starting vortex, and thus we don't need to enforce the Kelvin circulation theorem. However, in the unsteady panel method, you do march the solution in time, so you basically capture the entire unsteady situation starting from rest up to whatever velocity. So you capture the starting edge vortex or the starting vortex, and thus you have to make sure that the entire system circulation sums up to 0. So the boundary conditions that you need to meet for the unsteady panel method is no penetration again, the Kata condition, and finally Kelvin's circulation theorem. So let's look at the steady panel method, and essentially the diagram here shows the actual problem we are looking at. So we are interested in an airfoil at a constant free stream and at a certain angle of attack. So if this is your wing here at an angle of attack alpha, then you can describe your velocity vector in your wing's frame of reference. So assuming that this is your axis, if the free stream velocity is u infinity, then the u infinity vector here is simply just the component of this vector in the y-axis, or the vertical and the horizontal axis, which is simply u infinity cosine alpha and in the x-axis, and u infinity sine alpha in the y-axis. So in terms of implementation, so we need to make sure that we enforce the no penetration boundary condition. So assume you have some sort of surface and you have a collocation point here over which you enforce the no flow through boundary condition, which means that the flow velocity on the surface is purely tangential, which means that the velocity component in the normal direction, which is represented by this dashed line, is always 0. And we have some vortex here, okay? So let's assume that we have some free stream velocity. I'm drawing this an arbitrary free stream vector, u infinity. So this u infinity vector essentially, well, let me actually make it smaller so that I can draw the all right, so let's assume that this is here is the u infinity, or the free stream vector. The free stream vector will have some sort of a normal component that is normal to the curve shape that we have here, or the wing surface. This is simply u infinity dotted with or projected on the normal unit vector. So how do we cancel out this velocity such that we have no penetration? Now the tool we have is this vortex here. We can set the gamma of the vortex such that the velocity induced by the vortex, right? I'm just gonna name this u velocity uv. So this is the velocity vector of induced by the vortex on the collocation point. This velocity dotted with that same unit vector on the surface is the same, opposite but equal. Thus, we would end up with the projected velocity of the free stream on the normal direction plus the projected velocity of the vortex on the collocation point in the normal direction. These should sum to 0. Thus, we have enforced the boundary condition, the no penetration boundary condition. So I hope that this gives you a not so abstract idea of what it means or how we use the collocation point and the bound vortices. So moving on, now that we've sort of got this image, another important point in the panel method is that each collocation point is influenced by all bound vortices. So assuming that we are looking at this collocation point and we want to enforce the no flow through boundary condition on this collocation point, well, we have to we basically have to consider the fact that each collocation point, or this collocation point, for example, is influenced by all the bound vortices on your wing. So that makes it a little tricky, because then if you have some sort of a free stream component normal to your collocation point, you have to make sure, or you have to set the gamma vortex strength of each vortex such that the sum of the induced velocities of all these vortices on the collocation point exactly cancels with the free stream component normal to the wing. And you have to do this for each collocation point. So these 2 points essentially capture the essence of this algorithm or this method. All right, so here I'm gonna start talking about the steps. So the first step to this algorithm is making a function for computing the velocity at a point due to a vortex. Now, before you start, you need to figure out how to write a function that would give you the velocity induced by a vortex on a collocation point. So we're just going to start with the simple case of one vortex, right, and one collocation point. And our goal is to find the velocity of the vortex in the horizontal and vertical direction that is induced on the collocation point. So to start off, I'm sure you guys have went over this, but we can start by the stream function of a vortex, which is given by gamma over 2 pi natural log of r, where gamma is the strength of the vortex and r is the radial distance between the vortex and a point over which you'd like to get the velocity. And to turn this sort of expression into a Cartesian frame, we simply change r into the Cartesian frame. So r is simply just the square root of x minus xj squared plus y minus yj squared, where x and y are the positions of the collocation point or any point over which you'd like to know the velocity, and xj and yj, so this is x and y, and the position of the vortex is xj and yj. All right, so knowing this, we can simply find the velocity of the horizontal velocity by taking the derivative of the stream function in the y direction. So u is equal to d psi dy, or partial psi partial y, which, and I'm not going to go over the actual derivative. I'm just going to write it down, but it's basically just a simple chain derivative where the result is gamma over 2 pi times 2y minus yj, and then half x minus xj squared plus y minus yj squared power minus half, and then multiplied by 1 over x minus xj squared plus y minus yj squared to the power of half. So you can double check this expression. This is simply the chain derivative of this expression here, which simplifies to gamma over 2 pi y minus yj over x minus xj squared plus y minus yj squared. Okay, and in the same vein, v, which is the vertical velocity on the point, is minus partial psi partial psi partial x, which again I will skip the taking the derivative, but it simplifies to minus gamma over 2 pi x minus xj over x minus xj squared plus y minus yj squared. And putting this in a sort of a matrix form will give you u and v is equal to gamma j over 2 pi rj squared multiplied by the matrix 0, 1, minus 1, and 0, and then x minus xj and y minus yj, where rj squared is equal to x minus xj squared plus y minus yj squared. And all I did here was take this equation and this equation and put them into a matrix form. So I'm gonna circle that here, or not circle, just rectangle that. And you just can basically make a function, for example, that takes in the positions x and y, xj and yj and gamma j, and gives you u and v. So for example, that could be translated into a MATLAB function, u and v equal to vor 2d of x and y, which are the positions of the point over which you want to find the velocity, and then xj, yj, the position of the vortex that's inducing that velocity, and finally gamma j, which is the vortex strength. Or let me actually do some changing here. I'll just put gamma j first. Anyway, it doesn't matter what position you put it in. So now that you've built that, let's actually go to step 2. And that is discretizing the wing. So again, we've talked about the first step, which you simplify wing to camber line. So let's say you have a wing that is sort of looking like that. You simplify it to just its camber line. And when you simplify to the camber line, the second step is you determine the coordinates of the camber line. So for example, if you have axes here, right? We will say that this is x and this is y. We want to draw our camber. So this is our camber. Obviously, if you have a 0 camber, then the camber will be on the x-axis. So this is your camber, and you determine the corner points or the coordinates of that camber. So you basically just take the camber and discretize it to corner points here, just like that. And typically you want an even number of corner points, and I'll go over the reason for that a little bit later. So to talk a little bit more concretely, we need to figure out how to come up with a camber line coordinate for a specific NACA airfoil, and I'll go over it right here. So let's say you want to model a NACA 4-digit Sirius airfoil, which are one of the most typical airfoils used in general. So here, the equation set for the y coordinate of the camber line can be expressed as the following. Now we'll go over all these parameters in a bit, so do not fret. Okay, 0 and PC, and then so it's the equation for a camber line for any NACA 4-digit series is essentially a piecewise function. Okay, so here the x is obviously the position along the x-axis, and yc is the vertical or y-coordinate of the camber line. So basically a corner point here would have the position y, x, and yc. Now, M represents the maximum camber and P represents the position of the maximum camber. So M right here is max camber, and it is the 100. So if you want to back out the maximum camber value from the 4-digit number, it's the 100M is the first digit in the series. I'll give an example soon. And the P is the position of camber, and that, well, sorry, not the position of camber, it's the position of maximum camber. Position of maximum camber. And that is 10P is second digit. For example, let's say you are looking at some arbitrary NACA series swing, 1322. The first digit is 1, and thus M, the maximum camber, is that digit divided by 100. The digit 3 here is 3. The second digit is 3, which means that P, the position of the maximum camber, is 3/10. So you plug M and P into this equation and you can find your camber coordinates given the x positions of your corner points. All right, now that you've found your corner points, or your coordinates of the coordinates of your camber line, you can divide it into a series of bound vortices and control points. So that's the next step. Divide corner points to bound vortices and collocation points. And the way to do that is simply taking the first collocation point or the collocation point, the corner point at the leading edge, and saying it's a vortex. And then the one after that is a collocation point, the one after that is a vortex, and keep basically doing that. And obviously I did not pick an even number here, 1, 2, 3, 4, 5, 6, 7. Apologize for that. So I'm just gonna do here. Anyway, yeah, so you start with a bound vortex at the leading edge and alternate between bound vortices and collocation point, such that you have a collocation point at that trailing edge. And having a collocation point at the trailing edge is actually pretty important to enforcing one of the 3 boundary conditions, namely the cutoff condition, and I will go over that. All right, so in doing that, you will always end up, if you have an even number of corner points, you will end up with a bound vortex at the leading edge and a collocation point at the trailing edge. And here, let's say you picked number n. If n is your number of corner points, if you picked 100 for your corner points, then the number of bound vortices is 50, and the number of collocation points is also 50. And having an equal number of collocation points and bound vortices is important so that you have a system of equations that's not overly defined or underdefined, and this will be apparent later on in the lecture. And you have to find the unit normal vectors on the surface. So since we are interested in finding the normal components of velocities on the surface at the control points, or the collocation points, we have to come up with a system to define the normal unit vector on the surface of the camber line. And here I have a note on how to find the normal unit vector over a wing or over the collocation point. So in here, I'm assuming that we have 3 black points. Each black point is a collocation point. And this is one way of determining the unit vectors. You don't have to use that. You can use any other method. But basically assuming that the collocation point I minus 1 lies at the position of x vector I minus 1. So the x I minus 1 here is the position vector of this collocation point. And this vector is the position vector of this collocation point. We can simply find the tangential unit vector, which is equal to, and this is a first order approximation of the tangential vector. Because I'm only using I and I minus 1, you can come up with a way to get the tangential vector using some sort of a central difference method, so that you actually use I plus 1, I minus 1 in the limit of lots of collocation points and bound vortices. There shouldn't be a big difference, but use whatever method you prefer. But the tangential vector in this case would simply be xi minus 1 divided by xi minus ix minus 1. This is the tangential unit vector over the norm, or the magnitude of the difference between the two vectors. So this right here is the tangential unit vector of collocation point I, which is represented here. Now, to get the unit vector from the normal unit vector from the tangential unit vector, let's assume that this tangential unit vector comes out to this vector, a and b. If that's the case, then the unit vector, the normal unit vector, is simply minus b and a. And why is that? It's because the two vectors here, the normal and the tangential, should be orthogonal, and thus the dot product of ti and ni should equal to 0. Now, is it equal to 0 in this case? Let's dot a and b and minus b and a. This will equal to minus ba plus ba, which is equal to 0. Thus, these two unit vectors are orthogonal, and thus this is the right unit vector. And we can also look at it from a visual standpoint to make sure that it's pointing in the right direction and we did not get the negative of it. So if ti is b and a, right, assume b and a are positive. Thus b and a are pointing in this direction, right, because this is positive and this is positive. Thus, if we use minus b and a, that means now the x position of the normal unit vector, or the x component, is negative, and the a component is positive. So not only do we have the vector pointing in the right axis, but it's also pointing in the right direction and not pointing the other direction. But anyway, this is the formula for the unit vector, normal unit vector based on the tangential unit vector. So we're now at step 3. And step 3 pretty much entails setting up or set up system of equations to be solved. And keep in mind the first boundary condition that we want to meet is the enforcement of no penetration, i.e. the total velocity vector normal to the surface of at any collocation point is 0. So again, here we have a diagram that shows what I mean by that. So if you have basically a free stream coming this way, it has a component in the normal direction, and you want to set the strength of your vortex J so that the total velocity at collocation point I that's normal to the surface goes to 0. So this is actually pretty easy for the setup of one vortex and one collocation point. For this, for a system of one vortex and one collocation point, you simply have, so U and V here are the velocity induced by a vortex J on the collocation point I. Now, the component of that in the normal direction at the control point or collocation point added to the free stream velocity vector, again, component along the normal direction at collocation point I, goes to 0. So this here is the free stream component, and this here is the vortex component. Now, let's up the complexity a little bit. Let's say we want to look at the setup where you have all the vortices on the camber, but all you need to do is enforce the no penetration at, let's say, one collocation point. So let's pick just the first collocation point. Let's pick I equal to 1. So for all j, because j stands for the vortex, for all j and I equal to 1. And this here is just a simple schematic of what I mean. You have all the vortices on the camber line, and they all affect the collocation point of interest. In this setup, we basically will sum the influence for all j. So assuming that you have NV vortices, so you'll find the velocity component that's induced by all the vortices. You find that component again in the collocation point of interest, and then you add that to the free stream component that's normal to the collocation point surface, and that should equal to 0. So here I is equal to 1. So now let's up the complexity to the full problem. So we want to look at all vortices and all collocation point. All right, it's the same sort of equation again, so I'm gonna just rewrite it here. Plus u infinity dot ni equal to 0. However, I takes the values of 1, 2, and c, so all the control points. So what that looks like is given by the schematic here, where each vortex, well, each collocation point, so collocation point 1, is affected by all the vortices, but then again, all the collocation points are affected by all the vortices. So you end up with a system of equation. So a system of equations that is equal to the number of the collocation points. So if you have NC collocation points and NV vortex points, that means that you will end up with a system of equations where you have NC equations and NV unknowns, because essentially the vortex strength of each vortex point is the unknown parameter. So this equation system is only well defined if NC is equal to NV. If NC is bigger, that means you have more equations than unknowns. You have an overdefined system. And if NV, the number of vortices, is more, you have more unknowns than equations, so you have an underdefined system. So that's why we need to have equal numbers of control points and bound vortices. All right, so let's zoom onto this specific point here. So this is what, again, this is the velocity induced by a certain vortex J on a certain collocation point I, and that's dotted by the normal component on the surface so that you get the component of that velocity normal to the collocation point. So we will expand this a bit. And as we know, we've talked about before, the velocity induced by a vortex on a point can be described by the following equation or matrix equation. And I'm just, writing it again, the one we talked about earlier with the function vor2d, xi minus xj, yi minus yj. So this is basically u and v of ji dotted with ni. Now that could be simplified with gamma j, and then you use the function that you've already formed, but you set gamma equal to 1. So essentially, you want to get the coefficients that are multiplying the unknown gamma strength. So all you have to do is just set gamma equal to 1, which is essentially equivalent to this equation here with gamma being 1. Right, and this function takes in gamma equal to 1, and then the position of the collocation points in question and the position of the vortex that we are interested in. And then you dot this expression with the normal unit vector at that collocation point that you're using. So if we set this parameter to, if you set this entire thing to AJI, you end up with AJI gamma J. This is your unknown, and this is your, we'll call it a coefficient of influence. Before we continue, let me correct some mistakes I've made here. The correct indices are ij and not ji. So I corresponds to the collocation point and j corresponds to the bound vortex. So let me change all of them in here. Let's see if there's anything else. I just simply flip the indices, and it'll be apparent later why that should not be done. But again, all of this is really ij and not ji, so my apologies again. And finally, I'm going to go ahead and call this ij. So this is really aij, and this is aij. So just to give you a less abstract idea of what the system of equation looks like now, given the given the sort of manipulations we've done, the system now of equations from collocation point 1 through n, nc that is as follows. So A11, so the coefficient of influence of the first vortex on the first collocation point times the vortex strength of the first vortex plus A12, so that's the influence coefficient of the second vortex on the first collocation point times the unknown second vortex strength, and then you can just essentially have an arbitrary number depending. So well, you're going to have basically unknowns that are equal to the number of vortices you have, so you'll end up with A1 NV gamma NV. And that is essentially, again, if you remember the equations we're interested in, that plus the free stream component normal to that collocation point sum to 0, which means that this expression here, which again, this expression is equivalent to this expression, is equal to the negative of this expression, which I will put on the right hand side now. So it's the free stream vector that is normal to the collocation point number 1, so that's why I have a 1 here. Dotted with the normal unit vector at the first collocation point. And then let me erase that. And then you have, again, you do the same thing for each collocation point, and thus you will end up with NC1 plus ANC2. I forgot to put the gammas here, so let me track back. Gamma 1, gamma 2 plus ANC NV gamma NV is equal to minus, again, the free stream component at the last collocation point now, dotted with the unit vector at the last collocation point, which will basically correspond to A11, A12 plus until A1n, and then A21, and then you go down till A and C, and then 1, and then basically, okay, just fill in the blank here, A, N, C, and V, right here. That multiplies the unknowns, which are gamma 1, gamma 2, until gamma NV. And this is equal to your right-hand side vector, which is again the free stream velocity component normal to the collocation point at each collocation point, which is given by the following vector. Then you just go down until you populate the entire vector. NC dot, and I hope here it is really apparent how having a different number of bound vortices and collocation points will affect your formula. So if you want to invert this matrix and you have a different number of vortices and different number of collocation points, you'll end up with a non-square matrix, which could be problematic. Now after setting up the system of equations, we've only really explicitly enforced the no flow through boundary condition by making sure that the normal component of velocity at each collocation point goes to 0. So where have we enforced the cutoff condition? Now, We actually have enforced the kata condition implicitly by putting or inserting a collocation point at the trailing edge. And that means basically if we have a collocation point at the trailing edge, that means that there is no velocity in the normal direction because they all sum to zero. That must mean that any velocity at the trailing edge is tangential to it, and thus we have made sure that the flow leaves the trailing edge smoothly. Now, if there was a normal component to the velocity at the trailing edge, then that will mean that the total velocity vector at the trailing edge is not tangential, and thus the flow does not leave smoothly. So we have implicitly satisfied the kata condition by putting a collocation point at the trailing edge. So let us put this in writing. Enforcing no penetration at the collocation point at the trailing edge sets the normal velocity component at the trailing edge to zero. Thus, the velocity vector at the trailing edge is only tangential, which implies that the flow leaves the trailing edge smoothly, meaning that kata condition satisfied. Now, step 4 is actually solving the system of equation. Now, you've set up a system such that you have an A matrix that is populated with the influence coefficients. You have a big gamma vector, including the gamma or the vortex strength of all the vortices in your camber line, is equal to some right-hand side vector that contains the free stream velocity information at all the collocation points. All you have to do to solve the system of equation given is do a backslash RHS, which solves the linear systems of equation to find the unknown bound vortex strength. The final step is computing the lift. Now we know that the total circulation that's bound to the wing is equal to the sum of the bound vortex circulations of each bound vortex. So this is NV, gamma J. So you sum those up to get the total bound circulation, and then you know that lift from the Kata-Joukowski theorem is equal to rho free stream times the circulation that's bound to the wing. And to get the coefficient of lift, non-dimensionalized lift by the dynamic pressure, like so, again, which is equal to rho u gamma total over half rho u infinity square times the chord length, which gives you finally 2 gamma over u infinity over c, which is the coefficient of lift of the steady state situation given by the panel method. And that's it. That finishes up the entire method. And again, I hope this was helpful. And if you have any questions, don't hesitate to email me.